Everyone, till now we have discussed about the different states transition of a process like ready, running, blocked or terminated. The OS will use one more kind of state. That state is called as suspended state. So this suspended state is different from the blocked state. So for example, if you are taking blocked state, this is the internal activity for a process. Whereas when we say suspension, this is the external activity happening in the process. So this suspension can be occurred in two cases. The first one is when a process is moved out of memory, nothing but if a process is swapped out, suspension may occur. Or else, if a user who has created this process specifies that this process should not be scheduled until some condition is satisfied, even in that condition, that process will be suspended. So, suspended is the fifth state which is used by the operating system, where this is a external to the activity in the process. So this suspension can occur in two cases: when a process is swapped out, and in the second case when the user is specifying that this process should not be scheduled until some condition is satisfied. So this is the process states and state transition when we are using two swapped states. You can see here we are using two swapped states. One is ready swapped and the other one is blocked swapped. So here you have the transitions from ready to ready swapped and blocked to blocked swapped, right? We have two transitions from ready to ready swapped and the other one is blocked to blocked swap, which are cast when a swap out action. So swap out action is what? When the process is moved out of the memory. When the reverse, while the reverse will happen when the same process is swapped in, right? So we have the two states. One is ready swapped and blocked swapped. So ready to ready swapped and blocked to blocked swapped will occur when there is a swap out action. The swap out action is nothing but moving out of the memory. The reverse action will happen when it is swapped in. When it is swapped in. From blocked swap to ready swapped. From blocked swap to ready swapped. So this state will occur when the process, if it has requested for any resources, then if the resource has been granted, then it will have the condition from blocked swap to ready swap, even if the process is in suspension state, right? So we have suspension state which occurs in two cases. One is when the process is moved out of memory or when user is giving some particular condition. Here we have two transition. One is ready to ready swapped and blocked to blocked swap, which both will occur when there is a swap out action. So swap out action is nothing but moving out of the memory, where the reverse will occur when the swap in is happening. And the next state what we have, resource granted or wait completed, which is here. It will occur when from blocked swapped to ready swapped, and it will occur when a process, if it is requested for any resources and if that request has been granted, this state transition will occur even though if the process is in suspension state. We have taken the OS view of a process. We said that we have two parts in a OS view. According to the OS view, the processes are having two parts. One is process environment and the other one is process control block. So this process control block contains like ID, priority, state, PSW and contents of CPU register. So you can record this table. So this PCB are having different parameters like process ID. Process ID. So this is the unique ID assigned to the process when it is created, right? So next we have child and parents ID. For example, when a process is created by an OS, that main process we call it as a parent process, nothing but parent, and the ID what we are given for that parent process is nothing but parent ID. If that main process or parent process is creating other processes, then they become child processes, and for that processes also we are using child ID. Therefore we will be having child and parents ID. Next we have priority. So this priority is generally on number what we are giving to a process when it is created, where this priority will keep on changing during the lifetime of this process, or maybe the resources what it is consumed. Next we have process state. So this is the current state of the process. Next we have PSW and CPU register. So this PSW and CPU register, it will contain both of them, they will contain a snapshot. So snapshot nothing but an image of the CPU. The CPU contents. So that CPU contents of that CPU when it was last released, we say. For example, just think a process has been blocked or it is preempted. When in these two conditions, the contents of the CPU, like the various registers, control registers or the data registers what we are using, all that information has to be saved on CPU. And if that CPU information what we are saving, if that will be in the form of a snapshot or image, and it will be holded by PSW and CPU registers. Next we have event information. For example, just think we have a process PI which is been blocked, and this will be blocked when it is requesting an IO operation. Now the event information field in PCB of this process indicates that one of the device on this process has requested for IO operation. It will give that ID. It will give that ID who has requested for IO operation. When that IO operation is completed, then it has to be moved from blocked state to ready state. Next we have signal information. This says about the information which are concerning to the locations of signal handlers. Lastly we have PCB pointer. So this is like a pointer pointing to the list of PCBs. So that list of PCBs may be a PCB of ready processes or a list of PCBs of blocked process. So this is the different PCB field which are supported by an OS, like process ID, child and parents ID, priority, process state, PSW and CPU register, event information, signal information and PCB pointer. For example, if you want to execute more processes, under same application, then moving between the process or switching between the process, it creates more overhead, right? So now we need a program which makes us to execute the process, many processes simultaneously, nothing but the concurrent process has to be executed. For that we will go with threads. So threads are nothing but a program execution. The thread is nothing but a program execution which uses the resources of a process. When we say this switching, the process switching, there are two overhead we have. Mainly there are two components of overhead. One is execution related overhead and the other one is resource use related overhead. When we say execution related overhead, for example, we know process is what? It is nothing but execution of a program. Hence, when we are switching between processes, then the CPU has to first save the contents of the running process. If it is switching to the next process, first it has to save the contents of the current process and then it has to load the CPU state of the next process, right? This is like switching from running state to another state, running process to next process. In both the case, the CPU has to save the current and the next new one. When you have resource use related overhead, for example, we know when you have process environment, it contains the information concerning resources allocated to a process, right? And its interaction with other process. So it leads to a large size of process state information which adds to the process switching overhead. For example, if you take out the context save, scheduling and dispatching functions, we know. So event, occurrence of an event is nothing but event is what? Change in the state. When an event is occurring, it causes the switching from execution of one process to another process. So one is nothing but the running process. Running process you can name it as PI, and the new process you can name it as PJ, right? If both the running process and the new process, PI and PJ, they belongs to the same application, then they share the same code, data and resources, and their state information differs only in the values contained in the CPU registers and stack, right? So process is execution of a program and a thread is program execution which uses the resources of a process. So this is, you can see the threads in the process PI. The first diagram is saying about the concept. This one is to say about the concept and the next one is to say about the implementation. Diagram here you can see these curvy lines what we are using, they are the representation of threads. So these threads are belonging to the same process. Therefore, they are relying on the same environment, right? Environment of process Pi. So these threads will have their own stack and CPU state. So they will have the same process share code. The same process shares the code, data and resources with one another. So now you can see this process Pi is having 3 threads. So for these 3 threads, the kernel will allocate the stack and thread control blocks. We said the threads are belonging to the same process Pi. Therefore, these threads will be executed. These threads will be executed in the environment of Pi. So, the OS will save only the CPU state and the stack pointer while switching between the threads. While switching between the threads of the same process. They are belonging to the same process. When we compare this thread state and thread states and their state transition, they are analogous to process states and process transition. So in the previous classes we have discussed about the process state and their transition. Now we will just look into the thread states and their transition. So when a thread is created, it will be put in directly to the ready state because its parent process already has the necessary resources allocated to it. Then it enters to the running state when it is scheduled. This thread does not enter the blocked state because of resource request, because it does not request for any resource, right? However, it can enter the blocked state because of process synchronization requests.